Good morning, one and all. So this is the 11th lecture in electric and hybrid vehicle, which is professional 3, elective 3, professional elective 3. We are starting with electric drives. Today we are going to see two topics. First one is DC drive principle and performance, and combined armature voltage control. So this combined armature voltage control can be a 10-mark question. You have to draw the diagram, you have to draw the graph, and you have to explain. In previous lecture we have seen what is the fundamental principle of DC motor. So when a current carrying conductor is placed in a magnetic field, it experiences a force. So this is F is equal to B into I into L. So on this principle the DC motor works. So first we are going to see how does the DC motor perform, what are the different characteristics of DC motor, what are the types of DC motor, and towards the end we are going to find application of DC motor in EV field, that is in combined armature voltage control. So again I am telling you two very important questions. Number one, characteristic of DC motor, that is torque and armature current characteristic of DC motor, series motor, shunt motor, and next one is combined armature voltage control, which is used in EV. These two are the main two 10-mark questions. The topic that we are going to see is given in the next slide, so you can find out this is DC drives, principle of operation. Already we have seen in the previous lecture, but again we are going to see how does the DC motor rotate, what are the performance curves. So TA versus IA, NT, all those characteristics are there, and combined armature and voltage control, which is application of DC motor. Chopper control of DC motor is another topic which we are going to see in the regular lecture on Thursday morning, that is on 20th of April. So we are starting with DC motor drive. So this slide already you have seen, kind of this slide you have seen previously. That is, whenever I am saying DC motor means supply is DC current and DC voltage. So this motor is used in EV and hybrid electric vehicle. Usually whenever motors are used in EV and HEV, frequently they need to start and stop, because a car, if they are run in a crowded road or within the city, continuously they have to start and stop. So this is not the case when the motor is used in industry, because industry generally it is a continuous process. It works for motor, runs for 1-2 hours, and then it stops again, it takes rest for half an hour or so, again the motor runs. But when the motor is placed inside EV or HEV, maybe in every minute sometimes you have to turn on the motor or turn off the motor 3-4 times, or the frequency may be more. So specifically whenever I am saying that motor for EV or HEV application, it has to follow some 3-4 different or difficult conditions. Number one is high rate of acceleration, deceleration. Whenever you are on the hill, at that time you have to reduce the speed, increase the torque. That time we have to decelerate. Whenever you are on highway, smooth highway, you have to accelerate the vehicle. So we know that DC vehicle EV vehicle control is nothing but the controlling of the motor. So whenever you are on highway, you have to accelerate. That means you have to increase the input to the motor. Motor will be generating more power, motor will be generating more output, mechanical force, and vehicle will run faster. Whenever you are on hill or whenever you are braking, at that time you have to decelerate. High torque and low speed climbing. So I was just explaining in the previous point, that is, whenever you are going up the hill, at that time torque has to be increased, and at that time speed will decrease. So in this time torque is more and speed is less. Opposite happens when the gear is high. In the high gear, torque is low and speed will be high. So that we are finding in the third point, that is low torque and high speed cruising. So whenever we are cruising means whenever we are on the highway or so, at that time our torque will be low and speed will be high. And there is another very important thing which is said as the very wide speed range of operation are also the features of this vehicular motor. That means from very low speed to very high speed, everything has to be given, or everything has to be produced by this kind of DC motor. Next we are going to see what are the types of DC motors in case of EV or HEV. We have discussed in the previous lecture commutator motors. So whenever brush commutator arrangement is there is a spark generation, the motor becomes bulky. So all the type of conduction type of motor or normal DC motor, it's called as a commutator motor. And if you are removing the commutator, brush commutator arrangement, which is called as a BLDC motor or so, brushless DC motor, commutator is not there. In that case, the motor becomes light, its efficiency increases. But yes, designing brushless DC motor is a little tricky. And the main thing in brushless DC motor is we need to connect the rotor position sensor. That is an additional connection, or there is an additional circuit we have to connect in case of commutator less motor. Okay, so this is the difference between with commutator motor, without commutator motor. So with commutator motor, efficiency becomes a little less, friction is there, spark production happens, which is not safe for electric vehicle. But commutator less motor, in this case motor becomes lighter, but we need to connect an extra circuit which is called as a stator position control or stator position finding sensor. You have to connect in case of commutator less motor. DC motors are commutator motors, that means the first type with commutator, normal DC motor. They can be series excited, shunt excited, compound excited, separately excited, and permanent magnet excited motors. So whenever I am saying series excited or shunt excited, that means only one voltage source is supplying the armature coil as well as field coil. In case of compound excited also, one voltage source is supplying to all the coils. Separately excited means armature is getting supply from one voltage source, field is getting another supply from another voltage source. Now what is the job of armature and what is the job of field? Because we know motor principle, current carrying conductor placed in a magnetic field, it experiences a force. That means there should be a current carrying conductor. That is what is the job of the armature coil. Sometimes we are calling it as a series coil. And shunt excited. What is shunt? Shunt or field. The field is nothing but it is carrying the field current. And what is the job of field? This field actually creates a MMF, or it creates a magnetic field. So we have to create a current carrying conductor. Conductors are already there in the armature. We have to make some current flow through it through the brush commutator arrangement. So there is a current carrying conductor placed in a magnetic field. That magnetic field is nothing but an electromagnet that is produced by taking the current from the same supply, and it is actually given to the field coil. And we know electromagnet principle. In our childhood we have created electromagnet by using a battery and wire and a pin, right? So same kind of thing we have to do here, just to create a electromagnet. So whenever there is a current carrying conductor, whenever it is placed in a MMF field or magnetic field, it is going to experience a force, and that force is going to rotate the shaft of the motor. Separately excited, field and armature, they are getting supply from two different sources. In that case the controllability becomes better. So in case of armature voltage current control, what we are going to see at the end of this lecture, we are going to use a separately excited DC motor. What is meant by permanent magnet excited motor? In this case, instead of the shunt coil, or in case of field coil, we are actually using permanent magnet. So permanent magnet excited motors or PM motors, they are not using any coil for generating the MMF, because instead of electromagnet we are using permanent magnet. So the material for permanent magnet is quite costly. That's why permanent magnet PMDC is little costlier, because it is using permanent magnet. DC motors need commutator and brushes to feed the current into the rotating armature from a static power supply. See, power supply is a static thing. It's a sthir thing. Sthir means static. But armature, whatever we are finding, it's a rotating thing. Always it used to be my wonder that how from a static source or non-moving source, how can we give electricity, or how can we connect electricity to a moving armature? So in the previous lecture I have shown you a video. In that case we have seen that each or the bunch of the armature conductor, they are connected to a commutator slot, and some commutator slot is getting, in the process of rotating, it is getting touched by the brush, and whichever commutator slot is getting touched by the brush is actually taking the current from the external source to the commutator slot. So whichever slot is getting touched by the brush, and that slot conductor, that commutator slot conductor is going to get the electricity. So you can see the video which is shown in the previous day lecture. Here also we are going to see a small image. There also you can find out. So not all the conductors in the armature get electricity at the same time. Okay, so there may be some 10 or 12 pairs of conductors. So out of that, 1 or 2 might be getting electricity at the same time, but that is sufficient to make the armature move, and after another set of conductor, it keeps on getting the electricity and they keep on rotating. So such components require maintenance. That means I told you that brush keeps on eroding because brush is connected with commutator brush surface. There actually the erosion of commutator brush happens and spark is created at the brush commutator junction, and that spark is actually not safe for electric vehicle or hybrid electric vehicle. So that is a very big negative for using commutator type DC motor in case of EV. So that's why whenever we are using commutator less or brush less DC motor, in that case that spark generation is not there. So that is a prime advantage of brushless DC motor. So in addition, winding excited DC motors have low specific power density. Winding excited means electromagnet is being created by the field coil. Okay, so even then in those cases actually the coil becomes very bulky. Coils are very big whichever are generating the magnetic field, and that is actually reducing the overall specific power density. So what is meant by power density? How much output power is produced by how much weight of the motor. Okay, so numerator is more or denominator is less, in that case specific power density is increased. So if we are removing the coil, in that case we are actually making the motor lighter. So whatever power density it is producing, it will become bigger. So instead of the field coil, instead of electromagnetic field, if we can use PM type of MMF force generator, in that case actually we are increasing the specific power density. So even we are using we are not using the field coil, even then due to their mature technology and simple control, DC motor drives have been prominent in EV and HEV based electrical propulsion system, because the research is going on since long. Okay, hence DC motor characteristics. So there is series DC motor, there is shunt DC motor. Series DC motor, you have to remember, it is used mainly for very high starting torque. So for vehicles, starting of the vehicle, DC series motor is highly sought after. Cranes, hoist, lifts, wherever there has to be a jerk in lifting some weight, there we are using DC series motor. Where is shunt motor used? Wherever the constant speed application is there, there we are using DC shunt motor. So these two characteristics you have to remember. For very high starting torque, DC series motor. For constant speed, we are using DC shunt motor. Here is a classification of electric motor drives. You are finding that in the left side it is with commutator motor, that means conduction type DC motor, self-excited, separately excited. Self-excited means only one DC source it is supplying series and shunt, that means armature and field. Separately excited means two different supplies, DC supplies. One is supplying the field, another is supplying the armature, and another is called as a PM excited, that is permanent magnet excited. In PM excited motor there is no field coil, so PM excited motor is lighter. Right side there is a commutator less motor. In this case first is coming the induction motor. So induction motor is a AC motor. By induction principle the power is transferred from the stator to the rotor. So in case of induction motor, mainly the AC power is connected to the stator, and by induction principle the stator power, electrical power, is connected to the rotor. We will see in case of next lecture, we are going to see how the power gets transferred from the stator to rotor in case of AC motor. So there are two types of mainly induction motor, wound rotor and squirrel cage. Squirrel cage is more widely used. So these are actually giving more power. There is single phase induction motor, three phase induction motor. Single phase induction motor, best example is the pump that is generally there at our home bungalow, where we lift the water in the tank. There generally we are using 1 HP, 2 HP. Single phase induction motor, and three phase induction motors are generally used in the industries for the same purpose of mechanical load rotation, but they are of high power. There are other motors, synchronous motor. Synchronous motor is of three types: wound rotor, PM rotor and reluctance. Synchronous motor is a motor, obviously AC motor. It rotates with synchronous speed or doesn't rotate at all. If I am saying synchronous speed, that is 120 F by P. If I say the synchronous speed is 1000 RPM, induction motor will rotate with little less speed than synchronous speed. So if 120 F by P, F is the supply frequency, P is the number of poles, so 120 F by P, if it is 1000, let's say, induction motor will run at 980, 970 RPM. But synchronous motor will run either at 1000 RPM or it will stop. So synchronous motor always tries to rotate with synchronous speed. Then under commutator less motor, there is PM brushless motor. So this is the most widely used motor in electric vehicle, that is permanent magnet brushless DC motor. So it is very light because there is no field coil, because permanent magnet is used. It is very light because brush commutator arrangement is removed. So PMBLDC, you have to understand, you have to study, and this is the most widely used motor in case of EV, PMBLDC. Then there is switched reluctance motor, SRM. So this will be the last lecture of this topic, module number 2. That is SRM we are going to study. And there is something another called as a PM hybrid, that is permanent magnet hybrid type of motor, which is not there in our syllabus. So we will be studying 3 types of motor. One is DC motor, another is induction motor, and another is switched reluctance motor. Also we will study afterwards the PMBLDC motor. So technological developments have taken commutatorless electric motor into a new era. Advantages includes high efficiency, high power density, low operating cost. They are also more reliable and maintenance free compared to the commutator DC motor. Why they are reliable and maintenance free? Because there is no friction and there is no spark generation. That's why they are maintenance free, and that's why they are more safe. Thus commutatorless electric motor have now become more attractive than with commutator motors. So with commutator motors were initial motors, commutatorless motors are present day electric DC motors. DC motor drive principle, we have seen it in the video. So first thing is F is equal to BIL, that is mechanical force with which the shaft rotates. So shaft is nothing but connected to the armature. So here you can find that here I am showing 2 conductors. Okay, they are around 90 degree apart, and 2 conductors are connected with 2 commutators. So this is the first commutator, second commutator, and this point is the brush. Okay, so here the positive is connected, here the negative is connected. So this is the external static supply. So from this supply electricity comes to this brush. So this smaller portion is brush, this is static, but this commutator is actually rotating, and whichever point of the armature coil is connected with the commutator, that part of the armature coil or armature conductor is getting electricity. So if you see from the positive through the brush, it comes to this commutator segment, then it flows through all this conductor like this. Okay, and then it comes to this segment of the commutator. From there another brush. So brush are the collector, so brush are the transmitter and receiver, you can say, but they are connected to this commutator. Now this is the surface where the static brush and rotating commutator, they are actually having a friction, and at this point you will be finding there is a spark generation and erosion of brush. So what is brush made of? Brush is made of graphite. Graphite is a very good conductor of electricity and a bad conductor of heat. Okay, so this brush keeps on getting eroded. So after usage, after few months or so, we have to keep on putting a new brush. So it is like a break of a cycle. So purane zamane wala cycle, the brake shoe keeps on getting very smooth. So we have to change the brake shoe after a few months time, or at least once or twice in a year. That concept you can apply here. And this commutator and brush surface, here actually spark is generated, which is not good for the safety point of view of EV. So DC motor drives have been widely used in application required adjustable speed regulation, frequent starting, frequent braking, reversing, and all those things. Various DC motor drives have been widely applied to electric traction. Traction means it is a vehicular application due to their technological maturity and control simplicity. So mechanical force, F is equal to B into I into L. B is nothing but the magnetic flux density. So this is the north pole, this is the south pole, and this is called as a pole shoe. And this north pole and south pole, they are having windings. So windings is not shown here. So only the faces of the electromagnet is shown here, but they are actually wound with some kind of coil. And whichever electricity I am giving to the armature through the commutator, the same electricity can be connected to these coils, which are wound on this north pole and south pole. So a part of the armature current goes to the field, and that is called as a field current, and that is producing this electromagnet. Now between north pole and south pole, from north to south, that is the direction of MMF. So this B actually is shown like that. B is the direction of MMF, that is the magnetomotive force or flux lines, and B is called actually the flux density. So more current you are giving to this armature will be generating higher torque, and accordingly. So the mechanical force, F is equal to B into I into L. B is the flux density, I is the armature current, and L is the length of the armature conductor. So when the wire makes a coil, the force acting on both sides produces armature torque. This torque is equal to BIL cos alpha. So this conductor is continuously rotating, and from this horizontal, whatever is the angular position of this armature conductor, that thing is called as alpha. So whenever this conductor is exactly 90 degree with respect to this flux lines, in that case cos alpha means cos 90, it will become 0. Okay, and whenever this conductor is exactly parallel with respect to this flux lines, at that time maximum amount of torque will be produced, which will be rotating the armature conductor. So this is actually the principle of DC motor, and motor principle is actually given by Fleming's left hand rule. So you just trace 3 fingers of your left hand perpendicular to each other. First finger gives you the direction of current, that means which one is positive, which one is negative. Obviously through the circuit current always flows from positive to negative. So direction of current means if I am just stretching my first finger, the base of the first finger is positive and the tip of the first finger is negative. Okay, and in between there is the circuit. What is meant by direction of MMF? Direction of MMF means which position is north pole and which position is south pole. So here you are finding the direction of flux from bottom to top. Okay, here bottom is north pole and top is south pole, likewise. So the operating principle of a DC motor, when current carrying conductor, so you are finding this is the current carrying conductor, this is placed in a magnetic field, and this armature conductor actually experiences a force, mechanical force, which moves or which rotates this conductor. The acting force is perpendicular to the wire and the magnetic field. So a better video was shown in the previous lecture, and this diagram actually is from the book of Ehsani. Definitely I am not going to ask you this question, that how does a DC motor rotate. I will not be asking you this question in the exam, but you have studied already this thing in your first year, so you should know how does a DC motor rotate. Okay, so read it from Ehsani book or understand the previous day video. It will be sufficient. What we are going to do is, what is alpha actually is written here. So angle between the coil plane and the magnetic field. If the alpha is more, at the time cos alpha will be less, torque produced will be less. DC motor constructional details. So the magnetic field may be produced by the set of windings, which is called as a field winding, or it is called as a wound field DC motor, which I am calling as a field coil, and permanent magnet. So either it is by field winding. If field winding is not there, you want a lighter motor. In that case you have to use PM type of, that is permanent magnet type of DC motor. The coil carrying the electric current is called as armature. Okay, so armature is carrying the electric current and field is carrying the current, which is directly proportional to the MMF density which they are going to produce. So there are two fields, one is electrical field, one is magnetic field. They react and they produces another field, third field, which is called as a mechanical motion. That is generally given by thumb in case of Fleming's left hand rule. So in practice, the armature consists of several coils to obtain continuous and maximum torque. Slip rings and brushes are there which are helping the current to go from a static source to the rotating armature. The performance parameters of DC motors are armature voltage, back EMF, and field flux. I think you know all these parameters. The type of wound field DC motors are here. So you can find here, this is a wound field DC motor, and this is a separately excited DC motor, because VA is the armature field voltage and VF is the shunt field voltage or magnetic field voltage. So VA, if we control, we are going to control how much is the armature current. VF we are going to control how much is the flux density. So this is a separately excited. Here it is written this is separately excited because field and armature both are connected to two independent sources. Right side we can find out a separately excited is in the left side, but right side we can find out a self-excited motor, because only one supply is there, VA. So this is a self-excited motor because same supply is giving supply to the series coil. So it is generally given as S1 S2. This is the armature coil, this is called the field coil, S1 S2. It is also called as a shunt coil or maybe field coil, something like that. RF, this F is very important, F stands for field. Okay, and this is the armature conductors which is having a resistance. I told you in the class that generally armature resistance is very small. Okay, 1 ohm, 2 ohm, 4 ohm in that range, but field resistance is generally big. For series motor it is around 10-12 ohm, but for shunt motor field coil resistance is in hundreds ohm, 50 ohm, 200 ohm, like that. In series motor, IF is equal to IA. We are finding that VA and S, that is field, coil, armature, all are in series. So whatever is the armature current, that is same as field current. So IA is equal to IF, that is series motor. Hence the field flux B is a function of armature current. So we can say that whatever is the flux density B, that is proportional to generally IF. IF is the field current, and here IF is equal to IA. So for DC series motor, B is proportional to IA. That is what they are saying, that is flux density produced inside the motor is directly proportional to armature current. This is a very important thing, that why, so you can write it down, that why DC motor is producing very high starting torque. So we are finding that torque generally is given by one equation which is given here, armature torque. That means with how much rotating force the armature will rotate. Armature is nothing but directly connected to this conductors which is at the rotor. So with how much bigger force the armature will rotate, actually that is given by the TA. T stands for torque Newton meter and A stands for armature. So armature torque is a function of flux, that is the flux density B, and which is actually directly proportional to IF, that is the field current, and multiplied by IA. KE is a proportionality constant. So armature torque is a function of, in case of series motor, armature torque is a function of field current as well as armature current. Now field current is proportional to phi and armature current is given by IA, but in case of series motor, what we are finding is phi is directly proportional to IF and IF is directly proportional to IA, because there is only one current in the series DC motor. So IF is equal to IA. So what we can say, that TA is equal to KE into IA square, which we are showing here. I think you can understand, because phi is directly proportional to IA, T is directly proportional to IA. So you can find out, instead of phi, if you substitute IA, you are finding TA is equal to KE into IA square. So TA is equal to K into IA square. This is a square graph. That means 1 unit change of IA, it will be generating square of 1 unit of current. Suppose IA is 1 ampere, TA will be 1 Newton meter. IA is 2 ampere, TA will be 4 Newton meter. IA is 3 ampere, TA will be 9 Newton meter. So this is what is called as a square graph, and this is actually a non-linear torque region. So hence we are finding that at the starting part, that means when IA is very small, a little bit of increment in the armature current is generating huge increment in the starting torque in case of DC series motor. This is happening only because of DC series motor, because for DC series motor, IA is equal to IF. But there is a catch. This region will not go forever, because initially when the magnet is not saturated, which magnet? Field magnet, which is produced by RF. Okay, so this magnet, as long as it is not getting saturated, phi and IA, they are proportional. So this equation, whatever is shown below, phi is directly proportional to IF or phi is directly proportional to IA, this equation remains as long as the field coil or field magnet is not getting saturated, because there is no magnet which will be giving you higher and higher and higher magnetism till any current you can input. So there will come a saturation point. After that, even if you are increasing the current flowing through the coil is not going to increase the magnetism. So phi will get saturated. So till the phi gets not get saturated, till the phi doesn't get saturated, TA is proportional to IA square. But what we'll be finding is, as soon as the phi gets saturated, why phi gets saturated? Because even if we are increasing the current through the coil, it is not going to increase magnetism. So up to a certain point, phi will become proportional to IA. After that certain point, phi will get saturated. In that case, we will be finding that phi will be a constant. So phi will get multiplied with this constant, and now this K is actually having a constant phi in it. So in that case, TA will become constant into IA, because phi has already got saturated. So here it is said that, so flux start building inside the motor initially, IA starts increasing with TA. At a certain value of IA, the field magnet and phi become saturated. So before this point, TA was equal to IA square. After this saturation point, TA is directly proportional to IA. That means initially it was a nonlinear square graph for TA and IA. After the saturation, it will be a linear graph between TA and IA. So initial part, it will be a square kind of graph, and after saturation it will be a linear graph, because TA proportional to IA, it is like Y is equal to mx, that kind of thing. So that's why we are saying that both these regions are shown in TA versus IA graph. And a very important question, I might ask it in the exam for 5 marks, that is, show the two regions in the DC series motor TA IA characteristic. So what is TA? TA is in the y axis, IA is in the x axis. We are finding that initially, so this is the saturation point where phi is getting saturated. So before saturation, TA proportional to K into phi into IA. Phi is proportional to IA, so TA is proportional to IA square. This is the initial part of the DC series motor where little bit of increment in armature current is increasing the armature torque like anything. And this is the initial region which is giving us very high starting torque. So little bit of increment in the armature current and armature torque is increasing very heavily. But that does not happen forever. At one point phi gets saturated. After that point, even if you are trying to increase IA very heavily, this is not going to increase TA very heavily. Okay, because after this point phi becomes constant. So in that case, TA becomes proportional to IA. So this is equal to y is equal to mx. This part is linear region. So this whole characteristic of TAIA in case of DC series motor is divided into two parts. Before saturation point, it is square graph, very high starting torque. After this saturation point, it is linear region. It is a linear increment of armature torque with linear increment in armature current. So very high starting torque at the low IA is the characteristic of DC series motor. As IA builds up, TA becomes linear and low. So for the lower IA, torque is very high. For the higher IA, torque is moderate. This is characteristic of DC series motor. There is another characteristic of N versus IA. That means how the speed changes with respect to armature current in case of DC series motor. We are finding that if the load increases on DC series motor, that will try to increase the armature current, and if the armature current becomes very high and load becomes very high on the motors, speed actually decreases. So this is a characteristic kind of exponentially decreasing kind of a characteristic. This is the NIA characteristic. At initial IA, that means whenever the motor is starting, speed of the DC series motor is dangerously high. You are finding that this graph is falling from the infinity. So whenever the initial current, that means very small current, 0.2, 0.3, 0.4 ampere, in that case speed of the motor is dangerously high. As you are putting more load on the motor, you will be finding that speed of the motor is going to decrease and it is getting settled or steady state at a certain value. So this is NIA characteristic and left side is TIA characteristic. Both these two characteristics can be asked for 6 to 8 marks, and whenever you are explaining TIA characteristic, you have to explain two regions. NIA characteristic, only one region if you explain, it is okay. And as this is IA is proportional to phi. Why so? Because this is a DC series motor, so IF is directly proportional to IA and phi is directly proportional to IA. So for DC series motor, N phi characteristic is same as NIA characteristic. So actually I am showing two graphs, but actually I am actually explaining three graphs. So three graphs are T versus IA, another is N versus IA, another is N versus phi or N versus IF graph. So three graphs actually I am explaining. And N versus phi and N versus IA, both characteristics are same. At low current, speed is very high. At high value of current, let it be field or armature, the speed becomes very low. So this is a DC motor constructional detail. I think you can very easily find out this is a DC shunt motor. Why DC? Because supply is a VA, positive, negative. It's a DC supply, and this is this black things actually. This is brush. M is motor. This is the armature part. Inside this there is the current carrying armature conductor, and that is carrying current of IA. And you can find out this is called as a field or shunt field. This is parallel with respect to armature conductor, and this is actually carrying the current IF. But one thing you can find out, I total is getting distributed in IA and IF. So if you are trying to increase the value of IA, obviously IF will decrease. Like that it happens. So this is DC shunt motor, and this is a self-excited motor, because the same supply is used VA to supply for armature current as well as field current. So DC shunt motor is a constant speed motor, hence IF and IA are in parallel paths and connected to a common voltage source. Hence independent control of IF and IA not possible here. So you try to increase IA, automatically or indirectly that will affect IF. How do we control IA and IF? We connect some rheostats here. Rheostat is nothing but a variable resistor. If you cut this resistor, rheostat resistor, you are going to increase IA. If you are cut this resistor in case of field, you are actually going to increase the value of IF. So we put some variable resistances in the armature path as well as field path. And how much is the armature resistance? It is 2-4 ohm like that. How much is the field resistance? It is around 50-100 ohm like that. So efficient method is to use chopper. So this is actually rheostat control and chopper control. Chopper control we are going to see next day. Chopper is nothing but a DC to DC converter. Okay, so we are going to see chopper in detail in the next lecture. So two ways you can control a DC motor: rheostatic control, which is a mechanical control. You just put two rheostats here, you keep on changing the value of resistance by the rheostat, the way we regulate the fan at our home, but that is a AC motor, single phase AC motor. We just keep on inserting some resistances in series with the motor, and that actually regulates the current flowing through the motor, and it increases or decreases the speed of the motor. Okay, the same thing can be done here. You just cut or you add some rheostatic resistor in armature as well as field. But more smarter, more electronic, better electronic control or precise control can be given by DC to DC converter. The DC to DC converter can be actively controlling and produce the proper armature and field voltage for a certain speed. So whenever you are going to control the DC motor speed by using a microcontroller, in that case you will be using better you use DC to DC converter. And you can find that the top diagram is a self-excited DC motor. Here actually another thing is shown. It will not be asked in the exam, but you should know that what is meant by a compound motor. So compound motor actually is capturing both the positives of series DC motor and shunt DC motor. What is the characteristic of series DC motor? It gives very high starting torque, it gives very high starting speed. What is the characteristic of DC shunt motor? It gives constant speed. So compound motor, you are finding this is the armature coil and this is actually the series coil. Okay, so this is a series coil, and so this arm looks like a DC series motor, and there is a shunt coil as well. So this is a compound motor which is having series coil, armature and shunt coil both. So compound motor is actually of two types. There is a series type of cumulative type of compound motor, and there is a differential type of compound motor. What is meant by compound? Compound motor is a motor where the properties of a series motor and shunt motor both are captured. So if the properties of series and shunt, they are additive, in that case it is called as a cumulative compound. If the properties of series and shunt, they are subtractive, that is called as a differential type of compound motor. Now this is another slide where DC series motor performance equations are shown. So V in whatever you are giving, that is actually IARA. So this is the armature resistance what we are saying, and this is carrying current of IA. Okay, and RA, I think field resistance, armature resistance, all the things are given together. So Vn is equal to EB plus IARA. What is meant by EB? EB is the back EMF. Back EMF is actually generating the output power. So whatever supply voltage you are giving, some part is getting lost at the armature copper, which is called as a IARA, and some part is producing the output. So this output is actually produced with back EMF. This is EB. And how is this EB reproduced? It is KE, constant, omega m into phi. Phi is nothing but the flux density, and omega m is the motor rotational speed. So this is the formula for EB. EB is equal to KE phi into omega m. I'm not going to ask all this thing in the exam. Only the characteristic of DC series motor is very important that you prepare. But this things, EB is equal to KE into phi into omega m, this you should remember, because then only you can control the motor, and then only with microcontroller or with your own laptop you'll be able to find out how to control or how to design the controller for a motor. So phi is the flux per pole in Webers. You can control this flux per Weber by controlling the field current, and omega m is the armature speed, radian per second. Sometimes it is called as a N. Okay, N is just speed in RPM, omega n is radian, omega m is radian per second. K is a proportional constant. TA is equal to K into phi into IA. For series motor we have found out initially phi is proportional to IA, so TA is directly proportional to K into IA square. That we have found out in case of DC series motor. So in case of DC series motor, phi is directly proportional to IA up to a certain time, and after that it becomes saturation. So all those two regions we have seen. So huge starting torque at the starting of DC series motor. This is the best choice for EV or EHV. and below whatever is given, you don't have to even remember that, just see what are the parameters which are controlling the output torque of a DC series motor. So it is Ke, Kf, they are proportionally constant, V in the external input, or it is called as a forcing function, Ra is the armature resistance, Ke, Kf again the proportionality constant, and omega m is the rotational speed of the rotational armature speed in radian per second. So what are the variables mainly for armature torque? So motor is generally known for its torque. Every motor is having a specification of torque, right? So that is actually a function of input voltage, armature resistance, and how much is the motor speed. So you should just remember all these parameters. It might be of use. Now there is the speed torque characteristic of DC series motor. You are finding that x-axis is the speed and y-axis is the torque. So it is a speed torque characteristic. Same we found in case of our in case of EV, or in case of IC engine based vehicle, we have found out y-axis was torque, x-axis was speed. So here you are finding the series motor. So initially you are finding that DC series motor is having very high starting torque, and as the speed increases, the torque decreases. Okay, so initially it is very high, and as the speed increases, the torque decreases. For shunt motor, you will be finding that initially also, so here it is separately excited or shunt. Okay, here also you are finding that initially the torque is very high, as speed is increasing, torque is decreasing, but you are finding that this thing x-axis, the variation of speed is very small. Okay, so that means speed is almost constant over all the region, right? In case of series motor, you are finding here speed is very high, here speed is very low. Okay, so there is a wide range of speed in case of DC series motor. But shunt motor, the distance, x distance between this top point and bottom point, it is very small. That means shunt motor or separately excited motor, they do not show very big variation in the speed. And compound motor, this is actually cumulative compound. You are finding it is in between series and shunt. So it is neither shunt nor series, it is in between that. Okay, so it is addition of two vector is producing the resultant. That kind of thing is cumulative compound. This will also not be asked in the exam. This is just to show you how to find out the characteristic of DC series motor. Now this is very important thing. I'm just giving a 1 minute pause so that you can understand what is this characteristic. So this characteristic you have seen already in case of simple EV, that is, it's a one gear system. X-axis was speed, y-axis was torque. You are finding that it is divided into two parts. First part is whenever you are starting the vehicle, there is a constant torque region. So this speed is called as a base speed. So till base speed, initial constant torque is maintained. After that, if the speed is increased, then you are finding the torque will decreasing, like that. So this first region is called as a constant rated torque. The second region is called as a constant power region. So constant torque region and constant power region. Obviously, if you want to keep the power constant with torque decreasing, so torque into speed is equal to power. So if the power is constant and torque is decreasing, that means definitely speed is increasing. I will repeat, initially the constant rated torque is there, torque is constant initially. After that, there is coming a constant power region. Power is constant with torque decreasing. So I told you that torque into speed is equal to power. So when the power is constant and torque is decreasing, means speed is increasing. So you are finding here the speed is increasing. So there are two controls what we are actually using. Initial control, when torque is constant, it is called as a armature voltage control. So in this region, actually you are controlling the armature voltage. You are not touching the field. So there are two coils. One is armature coil, which is the current carrying conductor, which is placed in the magnetic field. So initial part, you are controlling only the current flowing through the armature. So you are increasing the armature current, decreasing the armature, something, but you are only doing armature voltage control. That means you are increasing the voltage of the armature so that the torque remains constant. And after the base speed, in that case, you have to use field control. Field control means you have to control the field in such a way that the speed of the motor will increase. How it is done? This is explained in this circuit and in the next circuit. So from the graph I am explaining you have to understand these two parts. So first part is constant rated torque. In this case we change only the armature part. That means we might add resistance or subtract resistance from the armature circuit, and generally it is a self-excited system. You are finding here this left side is called as a armature control rheostat, right side is called as a field control rheostat. So initially what we are doing is we are actually adding a higher input voltage, or we are actually cutting the resistance. so that we are finding that the voltage is increasing and voltage is keeping the initial torque constant. And when it has reached this base speed, in that time we are changing the field rheostat. We are changing the field rheostat because whenever you are weakening the field, whenever IF is reduced, at that time speed will increase. That part we are going to see. So this is actually combined armature voltage and field control. What is the job of armature voltage control? To keep the torque constant between 0 to base speed. What is the job of field control? To keep increasing the speed so that the torque will reduce and power will be kept constant. Again, I am repeating the same thing. What is the job of armature voltage control? To keep the torque constant between 0 to the base speed. Base speed means where you are changing the gear. Okay, so up till from 0 to base speed you are in the first gear, and after that you are going to change your gear from first gear to second gear. Okay, like that. So it is a very simple thing. There is nothing difficult. So initial part is the armature control. This is the armature control circuit. This is the shaft. This is the load, actually the vehicle load is shown by the shaft, and this is the motor actually which is driving the EV. So initial part is controlled by armature, and latter part whenever your voltage, initial voltage is very high, torque is maintained, in the latter part you are changing the field and you are inserting the rheostat. You are inserting the rheostat and you are increasing the resistance so that IF is reduced. Whenever IF is reduced, speed of the motor is increasing. So let us go through all the points in the slides. Whatever I am explaining, the same thing you will be finding explained here in this theory. And a very important thing, this is a separately excited motor because you are controlling the speed and armature. You are actually controlling armature and field separately. So here you are controlling the armature, here you are controlling the field. Independent nature of armature voltage and field voltage gives more flexibility and better control of speed and torque. So in the first part you are actually keeping the torque constant. That means you are controlling the torque. You are changing the armature circuit so that you are keeping torque constant, because TA is directly proportional to IA. Okay, so if you are controlling the IA, at that time you are trying to keep the TA constant. So for EV, HEV, most desirable speed torque characteristic is a constant torque below a certain speed, which is called as a base speed, and constant power for a wide range after the base speed. So if you see the torque characteristic and power characteristic, you mix them, and this is the ideal characteristic of a EV. So what is the ideal characteristic? 0 to base speed, you are going to have a constant torque, that is the starting part of the vehicle, and after that whenever you are trying to increase the speed, at that time the power will remain constant. At that time torque will reduce. So this second sentence is very important. For EV, HEV, most desirable speed torque characteristic is a constant torque below a certain base speed and a constant power or for a wide range above the base speed. So you are finding from here, this base speed to here, speed is constantly increasing, torque is constantly decreasing, and power is actually constant, because power is equal to torque into speed. In a speed range lower than the base speed, that means in this region, speed range lower than the base speed, IA and IF are set at their rated values, producing the constant rated torque. So this is the starting point of the motor operation. So both IA and IF both are less. So initially you have kept the IA and IF both at a rated speed, rated value. That means a smaller value to get the constant rated torque. Now the armature voltage VA is increased to increase the motor speed. So you are finding here the speed will constantly increasing till the base speed, but torque is constant. Generally what happens is whenever we are increasing the base speed, torque will reduce, but in this case you are increasing the base speed but torque is constant. Why? Because in this case you are actually increasing the input voltage. So this is a very important concept which you have to understand, that now the armature voltage VA is increased between this region because we are increasing the speed from 0 to base speed, then also the torque is constant. That means from where this extra power is coming? Extra power is coming because now the armature voltage VA is increased to increase the motor speed. So between 0 to base speed, VA is continuously increased. So at base speed, VA reaches its rated value, that means maximum value. So whenever I am finding the very constant torque till the highest base speed, that means here we have connected the highest amount of input voltage to the armature. So what is the experiment? Once again, initially the armature voltage is less. We have set IA and IF at a set value. Then we are continuously increasing the VA value so that the torque remains constant. But that is also having a limit. So till base speed, even if you are increasing VA, the torque will remain constant, but VA is having a limit. You cannot increase VA after that. So initial part, this part actually, at here the VA, that is the armature voltage, it has reached its peak. Now VA is fully connected to the motor. So this is actually called as a armature voltage control. Now armature voltage VA is increased to increase the motor speed. At base speed, VA reaches its rated value. That means at this point VA value is highest, equal to V in. So whatever V in is equal to you are giving, that is equal to VA, and it cannot be increased any further. So VA peaks. What happens next? Separately excited DC motor. So now you are at this position, base speed, to further increase the speed of the motor from base speed. So initially you were increasing the speed of the motor by supplying more armature voltage to the armature. After this point, base speed, what you are doing is you are weakening the field. It is written here to further increase the speed from the base speed, because now I am taking the vehicle to the highway. Initially I just started the vehicle, I crossed the small lane of my home. Now I want to take the vehicle to highway and I want to have very high speed to the top gear. Okay, so field phi is weakened. That means you are actually reducing the field current. So that is the relationship. Lesser is the field current, phi will be actually speed of the motor will be increased. That is what we are finding. So you have to reduce the field current, or that will reduce phi, that will increase the speed. How? Because in this case what we are finding is we have to add more value of rheostat, more value of resistance. If you are adding more value of resistance, VF is constant, more value of resistance, IF will keep on reducing, phi will get weakened. If the phi is getting weakened, in that time the speed of the motor is equal to increasing. So the phi is weakened, it is done by reducing IF by adding, that is very important. So if you are adding resistance, in that case field resistance is increasing, in that case phi is getting weakened, IF is getting weakened, you are going to find that speed of the motor will increase. So this field control is achieved by the field rheostat. This is the field rheostat which is helping us to achieve the field control. So what is meant by armature control? Armature control in short is whenever we are increasing the armature speed by keeping torque constant, actually we are increasing the armature voltage. That is what is called as a armature voltage control. And what is meant by field control? That after the base speed is reached, we cannot increase the armature voltage anymore, but then we want to increase the speed of the motor. How can we do that? We can do that by reducing the phi. How can we reduce the phi? By reducing IF. How can we reduce IF? By adding more rheostat resistance in the series with the field coil. And as it is separately excited motor, VA and VF, these two are different supplies. Adding field control rheostat is not going to affect the armature side. So armature control is first for constant torque, and speed control is next for constant power. That is actually what is done by combined armature voltage and field control. So you have to draw this diagram, you have to do all this explanation in detail. Again you have to draw this circuit diagram, you have to show the armature side, you have to show the field side. All those things you have to show in detail. So to further increase the speed from the base speed, we are weakening the phi, we are weakening IF, we are increasing more speed. So in the field control, that means latter part, speed increases and torque reduces as power is equal to speed into torque. Hence output power remains constant after the base speed during the field control. So till base speed, torque remains constant. From base speed to the maximum speed, power remains constant, torque reduces, that means speed increases. This is a very important equations that you have to remember. This is the last slide. There is a speed torque characteristic of DC series motor or DC motor. Series DC motors are suitable for applications where there is requirement for very high starting torque, like crane, hoist, lift, and there is a engine. Initially huge kind of impulse kind of torque has to be generated. In that case DC series motor is used. Okay, so wherever the huge starting torque is required, heavy torque overload is required, such as traction, lift, hoist. In this case we are actually using DC series motor. So this was case for electric traction before the power electronics and microcontroller era. However, DC series motor for traction applications have major disadvantages. So there is very high starting torque which is offered by DC series motor. This very high traction application, that means initially huge pull, this application is having a major disadvantage. At starting of the motor, if the rotor is not loaded and full supply of the voltage is connected to the motor, dangerously high speed actually burns the armature conductor. So we have found in the characteristic, that is NIA characteristic, initially the motor is not loaded. That means no mechanical load is put on the motor and motor is started. What will happen is huge amount of current will start flowing through the armature conductor and armature conductor will burn. That is actually a very important, or that is actually a very big negative for DC series motor. And I think you have studied in the first year, that's why we are connecting a starter. So DC motor starter actually helps what? Starter actually reduces the initial very huge current flowing through the DC motor. This actually is reduced by the starter. And as the motor picks up speed, as then continuously we keep on cutting the resistance so that the armature conductor becomes safe. Okay, so there is a negative that they are explaining. That is, at the starting of the motor, if the motor is not loaded, in that case, and if full supply is given to the motor, dangerous increment of armature current causes the burning of armature winding. Motor starter is connected to save this problem of the initial start. So initial stage or starting part of the motor, DC motor, is actually saved by the starter. Major disadvantage of DC series motor is difficulty of regenerative braking. So regenerative braking is not well found in case of DC series motor. That is another disadvantage from EV or HEV point of view. Shunt motor is used where constant speed is the requirement. The speed torque performance characteristics of cumulative compound DC motor is in between series excited and shunt motors. So some of the EV, HEV, they use compound motor, cumulative compound motor for the propelling part. So this was about DC motor characteristic. This very important question is combined armature voltage control and field control. All these things are very important. Next day we are going to see the chopper control or chopper speed control for DC series motor. So this lecture finishes here. Thank you.